Welcome to videos on memories. So in the previous videos we have seen non-volatile memories, and they are all of read-only memory where we used to store the value permanently, and we could able to read it a number of times. Of course, we also saw that even for those ROMs, so there is a possibility of erasing the values, and then you can able to still rewrite it, so using exposing it to UV light or through electrical arrays. So next category of memories is RAM, that is random access memory. As the name itself indicates that you're supposed to randomly access the memory, so this is of a category where you can able to read as well as write the memory locations n number of times. So it's not only read only, so you can able to read as well as write the content of the memory. So under this random access memory, we have one of the category which is static RAM. So the value that is stored in this particular RAM will be held for a long time, as long as you are not changing. As long as the power supply is there, it is going to retain the value. If power goes, okay, you will going to lose the value. So in order to randomly access the value will be stored. If the value that is stored in a particular location is logic high, it will be there as logic high as long as the power is there. Okay, let us try to understand, okay, how can we just store a value of logic 0 or logic 1 in a static RAM. So let us go to the basic circuit of implementation of this RAM. So let us see the circuit diagram. So this will have a back-to-back connected inverter circuit. This is one inverter, and this is another inverter. You can see now you have two inverters, and this is connected to VDD. So this is similar to that of a SR flip-flop. This is connected to ground. This output is connected to the gate of this inverter, and this is connected to this. Now if you are writing this as Q, then naturally this will be Q bar. This will be Q bar. So this is basically a SR flip-flop. So SR flip-flop, you also going to have set reset inputs as well as the clock. So the basic structure is now for a static RAM is back-to-back connected inverters. Let us name the transistors as M1, M2, M3 and M4. Along with these 4 transistors for 2 inverters, let us have 2 more transistors by name M6, and there is one more transistor which is now M5, let me call it as. These are 2 more transistors. Now we will connect these 2 gates to one special input which is very specific to the memories, that is word line. So this is word line, and the bit lines, okay, as we discussed in the previous discussions, we're going to have word line, bit lines and all those things. This is the word line of this random access memory. Let us consider the bit lines also. So this is one of the bit line which is connected to the M6 as well as M5. I will write it as BL. This is also a bit line, but this is the complement of BL. So this is BL bar, this is BL. See, now this is a complete static uh, RAM. So we write it as simply SRAM. So a static SRAM consists of 6 transistors, out of which, okay, 4 are going for connecting a back-to-back inverters, and of course M5 and M6 are the pass transistor, which are again of N-type. So this is the circuit diagram of static RAM. So let us try to understand, okay, how do we read or write the values onto this. Okay, let me start first try to understand, okay, how do we store the value, how do we actually read the values. So let us assume that this is holding a value of 1, that is logic high is stored. So naturally when this is logic 1, that 1 is fed to this, then this transistor is on, and this transistor is on, we know that the voltage here will be 0 volt, or you'll be having a low logic being stored here. So what we are assuming is that, so let us assume that, so let us try to read a value of 1 that is stored in this particular transistor. So as long as 1 is stored here, so this 1 will make M1 transistor to turn on. When M1 transistor turns on, whatever voltage that is there will be get discharged to 0. This 0 will going to turn on this transistor. When this is on, you are getting this output voltage at Q will be VDD. So as long as you are not altering the values, as long as VDD is there, so this value of logic 1 at Q, and of course its complement at Q bar will be there forever. So that's why it is now static in nature. The value is going to be there as long as the power is there. Now let us try to see, how do I read this value? What is the procedure? Okay, how do I read the value that is there stored as 1 in the value of at Q, because naturally we know that since it is Q bar, it will be the complement of it. So for read operation, so first and foremost thing is that we're going to pre-charge the bit lines. So now you can see there are 2 bit lines. So there is a bit line BL and there is one more bit line BL bar. So during the pre-charge, during the read option, you pre-charge both BL as well as BL bar with high. So you are making this also high. Even though this is BL bar, you make this also as high. So I'm making both bit lines and bit line BL bar as high. So now you can see I'm making this as high. This is also made high. So this is the first procedure, or the first step you have to follow whenever you are doing the read operation. You pre-charge the bit line and bit line bar lines as high. Second one is you make word line equal to high. With this as high and this as high, now you make this word line equal to 1. When word line is equal to 1, this transistor M5 and M6 will turn on. So M5 and M6 are on now, So since M5 is on, M6 is also on, whatever high voltage you have, so now we can see this whatever VDD you have here will going to discharge through this transistor, and this whatever the pre-charge value which was high was there will become low. Whatever okay, logic 1 you had, that will become logic low because this is being get discharged. Now let us try to see what happens to this. So since this bit line was also made high, this is made high, you can see now whenever this is low, because the earlier this is high means, so this transistor is M4 is on, M3 is off. Since M3 is off, this cannot discharge to this M3 because this is the only path that is available. Since it is off, because the value that is read is equal to the value that was stored is equal to 1. Since it is off, whatever the pre-charge value that was there at BL will remain as high. Meaning after making this word line is equal to high, the BL which was pre-charged to high, which was pre-charged to VDD, will remain as VDD, whereas BL bar which was pre-charged to VDD will now go to 0 volt, meaning that after making this word line equal to high, you see what is the condition of your bit line and bit line bar after making this word line is equal to 1. Since we know that after making this word line is equal to 1, we are actually trying to read what is the content of this register. The content of this register is actually 1 here, so that's why your bit line is becoming 1. The bit line bar is actually 0 here. So you actually stored 0 here, this is stored 1. Even though this is 0 and 1, we say that this entire bit is storing a logic 1 is stored here, because this is the one which is basically read as the value that is stored, and of course it is its complement. So if the bit line h which was high, if it is retained as high, means so the value that is stored is actually 1. The value that is actually stored is 1. So assume that you store a value of 0. You store a value of 0 and you have a, of course, if it is 0 then this will be 1. You again make this pre-charge. So as I said here, suppose assume that now this is when the value of a stored value is equal to 1. Now with the store value is equal to 1, after that word line making 1, this is still remaining as high and this has become low. So since the value that on the bit line is high, so it is said that the value that is stored is 1. So whatever we have assumed, whatever that is stored will be read on bit line. So that's what is read operation. Now assume that stored value is 0, is 0 volt or low level or low logic. In such case, you again make BL and BL bar as high, make word line is equal to high. Once you make this word line is equal to high, because you can see since the value that is there here is 0, 0 means this is on. When this is on, you had a value of high here. This high will certainly be discharged to 0. Whatever value that you had 0 will be reaching onto this bit line, because the pre-charge, the value of your bit line was high. The bit line was high. Because of this, bit line which was equal to high will become 0 volt, because this transistor M3 is on. Why this M3 is on? Because the earlier case, if this has to become 0 means, so this M3 is actually on. So since M3 is on, so whatever pre-charge value on your bit line is 1 will actually go to 0, and of course this high will remain as high, because this is high means, okay, what is the condition of this transistor? If it is 0 means this is also 0 volt, then this will be off. This will be off. If it is off means this won't change. Of course this won't discharge. The value that remains will be remaining at the pre-charge value high. So bit line which was high is now becoming 0 volt, which is a low level. Bit line bar which was equal to, which was actually high, will remain as high here, will remain as high. Can you see here this just have a look at that. Okay, what is the value that is stored here? The value that is stored is 0 or low level. The value that is read is also low level, because value that is read on this word line will be available on bit line. So on the bit line you have, after that WL, after the word line becomes high, word line going high is actually mean to read the value that is stored in this bit. So the stored bit is 0, so you could able to read the same value of 0 here. So here we are just saying that okay, everything is fine, because we didn't so far we didn't consider the or dimensions of the transistor. So let us consider a case. So let us just revisit this with more specific dimensions of the MOSFET. So let me just rewrite the entire SRAM structure again. So this is my SRAM structure. So that now this is transistor, one inverter, and this is the second inverter. So I have this, so this is connected to this, and this is connected here, and you have this as VDD. Then I have a pass transistor which is in the form of M5, and I have one more transistor which is in the form of M6, M5, this is M6, and I have a ground here. This is M1, 2, 3, 4. So I have a bit line of this is bit line bar, this is bit line. So let us assume that this value that is stored is high here. The value that is on this side will be low. Since it is high, so this will be in on condition. Since it is low, this is in on condition. Fine. So let us try to see. Now let me make this high, make this also high, and of course this is my word line. If I make this word line equal to 1, so that means that I want to read the value what is there stored here. So we are assuming that this is high, logic 1 is stored in this particular bit. Whenever this is high, this is also high for pre-charge condition. Assume that this h, whatever h you have, if this h comes and sits here, suppose what we assumed was in the previous case, whatever high is there will going to discharge through this. Assume that if the discharge is not happening very fast, if the discharge of this high is not happening very fast, in such case, suppose assume that this is happening slowly, the value of this voltage which was low, if at all if it becomes equal to, if at all if this voltage goes high, so what happens, because you have 5 volt here, you have 0 volt. So since this 5 volt is connected to this, as long as the, as soon as the word line becomes 1, so then this 0 volt tries to go to 5 volt, and assume that this is having bit larger s, because if this 5 volt has to go to 0 means it has to discharge to this particular transistor. Suppose assume that M1 transistor is weak. If the M1 transistor is weak means if the resistance offered by this is more, then the voltage rises here. Then the voltage rises here. If the voltage rises here, you can see this will going to make this transistor or this voltage also go high. Initially this was low, that's why this was off. That's why this was off. Once the voltage rises here, because of this is weaker, this is stronger, what happens is the voltage here also rises, then this tries to become turn on. Whenever this turns on, this will become 0. So you are actually supposed to read the value which was high here, which we saw here. Okay, it will going to happen perfectly if everything is fine. Suppose if the dimension of this transistor is okay very less, and if the dimension of this transistor is more, meaning if M5 is stronger than M1, then something like this will happen. Then you are actually writing this logic 1 to this instead of reading. Now you are actually trying to write. So this is what is called as this actually is called as writing 1 into the cell. So you are actually you started actually reading the thing. Now you are actually started writing it to this transistor, because we are assuming that M1 is weak and M5 is stronger one. Suppose whenever something this whenever you are writing 1 during the read operation, then we call it this as read upset. The entire process of making this bit, both the bit lines as high and then making this word line equal to high, means it is to read the value what is stored. But instead of actually reading it, I'm actually writing this value because of this assumption. So assumption is that this is weaker, this is stronger. So in order to avoid this read upset, so why it is called as read upset is because I'm supposed to read the value which was written as, which was stored as high, but I'm ultimately ending with writing 1 onto this bit. Whenever 1 is written onto this, I'll ultimately have a 0 being stored onto this particular thing. So write 1 is nothing but you are writing 1 to this particular node, which is not desired in this type of read operation. In this read operation, as we explained in the previous case, the value of your BL should remain as high and this should go to 0 under normal condition. Because we assume this is stronger, this is weaker, you are in trouble. So the dimensions of transistors have to be very meticulously adjusted so that the voltage at this point should not go above the threshold voltage of this particular inverter. So we know that threshold voltage of this MOSFET is around 0.4 volt. Whenever you turn on this particular transistor, whenever word line goes high, the voltage at this point should never go above should never go above 0.4. So if it goes above 0.4, then this turns on. So let us try to understand, so what should be the dimension of this M5 and M1 so that this condition of this turning on never occurs. So for that, let us try to understand what is a ratio called as cell ratio. Cell ratio. Cell ratio is nothing but it's a ratio of, okay, let me write it as this as my CR. Cell ratio is nothing but a ratio of WBL of 1 by WBL of 5. WBL of 5. So we should try to understand this cell ratio. What should be this cell ratio so that we can have a proper operation, proper read operation, so that I should never end up with this read upset, or I should not be writing a 1 during the read operation. We'll see this in the next video.